Welcome to today's tutorial. Today's tutorial is about space spanned by vectors. And before we start looking at the task we're going to do today, let me give you some definitions here. So here we have the definition for the dimensions of vector space. And here we have the n. They are natural numbers from 1, it starts up till n. So r to the power 1. So this r here represents real numbers, and to the power 1 would mean one-dimensional vector space. So it means if you have dimensions in the vector space, let's say, or in the plane, you have here x dimension. So r would mean just a single r would mean that it's in one dimension, let's say to the dimension of x. And then if you have r to the power 2, it means it's a two-dimensional vector, and the r1 and r2 are elements of the real numbers. They're always elements of the real numbers. The elements of the vectors are always real numbers. Now, if you have r to the power 2, that means it's a two-dimensional vector. So it would mean it's in the xy plane or any two planes. And if you have r to the power 3, then it's three-dimensional vector here. So let's say x, y, and also you have z. So it's a three-dimensional vector. You have three values from three dimensions, r1, r2, and r3. And you could have up till n-dimensional vector. So that's shown here. R to the power n would mean n-dimensional vector space. Now, here we have the definition for vector span. So m, again, it means any numbers, any natural numbers from 1 up till n. And v1, v2, vm are n-dimensional vectors. So they could be of any dimension. So here there are examples of v1, v2, vm, which is starting with a11 up till an1. So n dimensions. If you say span, or if you look at this set here, which is span of v1, vector 1, it means that it is lambda times v1, and the lambda is any element of the set of real numbers. So what does that mean? That means that if you have here a vector, let's say, if you have a vector 2, 1, so here, let's say this is our point. So that's the vector we have v1. Now, any other vector on this particular line, let's say, let's draw the line with a different color. So here we have, let's say, so any other vector on this particular line, which is lambda times the vector 1, 2, sorry, not 1, 2, 2, 1, is in the span of the vector 1, 2. So if you have a vector v1, which is 1, 2, as you can see here, this is the vector 1, sorry, again, I'm saying that, it's 2, 1. So if you have a vector 2, 1, any other vector on this particular line is actually a number lambda. So if it's here, let's say it's maybe minus 2 times vector 2, 1. So minus 2 is your lambda. So lambda times the vector itself is in the span of the vector 1, 2, 2, 1, sorry. So that's what the first definition here is saying. And then the second definition is saying the similar thing, which is span of now two vectors. So if you have two vectors, it would be lambda 1 times the vector 1 plus lambda 2 times the vector 2. And This would mean that if you have two vectors here, let's say 2, 1 again, and you have another vector, let's say -3, 1. So in the span of these two vectors, that is lambda times any, it could be positive lambda times the vector 2, 1, or negative lambda times the vector 2, 1, plus lambda 2 times this vector here, which is -3, 1, is spanning the area for the vectors of v1 and v2. And the lambda 1 and lambda 2 are real numbers. Okay, so if you have, let's say, m or until vector vm, and you're in the definition of the span of this set would be the set which says lambda 1 times v1 plus lambda 2 times v2 until lambda m times vm, where all the lambdas are elements of the real numbers. And this is how it looks like if you show it in the definition form. So you're just placing the v1 with the vectors actually here, and that's how it looks like. Now we can go ahead and try to see what's our question 1 for today. The question 1 is saying consider 4 and is equal to 3-dimensional vectors where you have vector 1 which is 1, 3, 4, vector 2 which is 1, 1, 3, vector 3 which is 1, 4, 0, and vector 4 which is 1, 6, 1. And they're asking the question, is the vector 1, 4, 2 in span of the vectors of the set of vectors of v1, v2, v3, v4? Now, if you're trying to solve this particular question, so just what we just looked at was, I just wrote it down here again. So we just saw that our question is spanning 4 vectors. So that would mean by definition that it looks something like this. That's lambda 1 times v1, lambda 2 times v2, lambda 3 times v3, lambda 4 times v4. And if you display the vectors, this is how it looks, right? Now, let's take our vectors and try to put into this one here. So what we just said is that, or what the question just asked was, is the vector 1, 4, 2 in span of the set v1, v2, v3, v4? So if it is, then the vector 1, 4, 2 will be equal to lambda 1 times the vector 1, which was 1, 3, 4, plus lambda 2 times the vector 1, 1, 3, plus lambda 3 times the vector 1, 4, 0, plus lambda 4 times the vector 1, 6, 1. Now, instead of calling them lambda, let's just call them x1, x2, and x4. So this is x1, x2, x3, and x4. You could just call them anything. I'm doing this for a purpose, which you'll see in some time. So here, if you try to solve this part here, or try to put the x inside the vector, so it would be x1, 3x1, 4x1, plus we have here x2, 3 times x2, plus x3, 4 times x3, 0 times x3 is 0, and then we have here 1 times x4 is x4, 6 times x4, and 1 times x4. And now if you add them all, it looks like this. So you have x1 plus x2 plus x3 plus x4. And here you have 3x1 plus x2 plus 4x3 plus 6x4. And here you have 4x1 plus 3x2 plus we have here 0x3, so I'm not writing that, and here we have x4. And this is equal to the vector 1, 4, 2 or not. That's what we're checking. So as you can see over here, very clearly, it looks like a system of linear equations, right? Let's write them down. So what we just saw is that we have here x1 plus x2 plus x3 plus x4 is equal to 1. And then we have here 3x1 plus x2 plus 4x3 plus 6x4 is equal to 4. And here we have 4x1 plus 3x2 plus x4 is equal to 2. So those are system of linear equations, and those can be solved using, so this can be solved using Gaussian elimination. And we have already learned how to do that, right? In fact, I've solved an exact example as this system of linear equations in one of the tutorials. I'll link the tutorial below this video, but let us still go back to the solution here. So this is exactly what we have now, right? This is exactly the system of linear equations that we just saw, and we solved them using Gaussian elimination. Okay. And we found out that there are infinitely many solutions here, right? So we have seen that we have infinitely many solutions here, which is for x1, we have 2 divided by 3 minus any real number r. And for x2, we have minus 2 divided by 9 plus any real number r. For x3, we have 5 divided by 9 minus any real number r. And for x4, it's the number or any real number r. So what we did was we tried to put some real numbers as we wanted. So we just used here r is equal to 0, r is equal to 1, and r is equal to 2 divided by 3. So when we use r is equal to 0, we got x1 as 2 divided by 3, x2 as minus 2 divided by 9, and x3 as 5 divided by 9, and x4 as 0. And r1 gave us different solution, r2 by 3 gave us different solution. So any of these values could be our lambda values or x values, as you saw. Let's go ahead and write this maybe down. It's a little more clear to you all. So what we are saying is that 1, 4, 2, if it is in the span of the vectors v1, v2, v3, v4, then we have some lambda values that if you multiply to these vectors, it's true here. And we just saw that there were a lot of solutions. So one of the solutions is lambda 1 as 2 divided by 3 times the vector 1, which is 1, 3, 4, plus lambda 2 as minus 2 over 9 times the vector 1, 1, 3, plus we have 5 over 9 lambda 3 times the vector 1, 4, 0, plus x4 or lambda 4 is 0 times 1, 6, 1. This was the first solution when we took the r is equal to 0. But this could also differ. This could be, we could take the second solution that we just saw here. The second solution is minus 1 over 3, 7 over 9, minus 4 over 9, or 1. And also the third solution. Any of them is right here. So this could also be minus 1 over 3. This could also be 7 over 9. This could be minus 4 over 9, and this could be 1. So this is one solution set. This is another solution set that we can get here. So as you can see, we have real numbers for lambda values here. So we can say that yes. So therefore, yes, the vector 1, 4, 2 is an element of the set span of the vectors v1, v2, v3, and v4. And that's the end of the first question.